Sorry for the delay. Looks good. All right. Hi. I'm Brandon. I'm an engineer on the iOS core experience team at Pinterest. And today I'm going to talk about composable caching in Swift. And if you don't know Swift, it's OK. If you're using a functional language that's decent, you can do all the things that we're going to talk about here. So why do we care about caching? Getting stuff from the network is slow. Getting stuff from disk is a little bit faster. Getting something from memory is very fast, but we have very limited memory, limited disk. So when we actually want to retrieve something big, or something where latency is important, we want to associate it with a key, and then and store it in these layers. And when we retrieve it, we go through this process. Okay, so a key goes in. We first check memory. If it's there, we return the value. If it's not there, we check disk. If it's on disk, we write back to RAM and we return the value. If it's not on disk, then we hit the network. If hitting the network fails, then we fail. If hitting the network succeeds, then we write to disk and we write to memory and we return the value. Okay? And sorry, this is in the context of like a mobile application, right? So we're getting, let's say, an image. Okay? But the same sort of process works on the back end as well. Okay? So key goes in. We might have some map, some dictionary on one particular machine. If it's not there, we might fall back to memcache, which is shared across a bunch of servers. And if it's not in memcache, then we might have to make an expensive RPC call to our data store service. But at the same time, whenever one of the layers succeeds, we write to the layer above, right? So let's look at more examples. Okay, image caching. URL of an image is the key. We look for a bitmap in RAM, and we look for a JPEG on disk before hitting the network. For video caching, if you're doing stuff on, if you're making an iPhone app, for example, the memory layer is handled to you by your framework. So you only need to care about the disk. So in this case, we only have a disk above a network. But even model caching can be thought of in this way. So for this example, we have a user profile, and our key is a user ID. We look up the structured profile data in memory, and we fall back to JSON on disk and JSON over the network. Okay? But in all these cases, we have this same sort of structure. We have these individual pieces that we're stacking on top of each other. And in the video case, we only care about the disk and the network. In the other cases, we care about that extra RAM part. But I've drawn the boxes in this way for a reason, because it's not just useful to treat the disk and the network as one type that you can instantiate multiple values for, but it actually makes sense to have one instance of our disk and network layer and share that across all of our caches in our application. And reason for that is that for inherently shared resources on your system, if you have one instance, one thing in your application communicating to that resource, things become easier. I'll make this more clear. So disk, okay? For our cache, let's say, our disk layer of our cache, we only want to store 1 gigabyte, okay? If we have one single object, let's say, that is responsible for writing to that gigabyte of space, when we get up to the edge, we know what to do. We know when we're over. We know when we're about to go over. If we have multiple managers talking to our disk, then when you get close to the gigabyte, you either sacrifice correctness, if you're OK with going over a little bit, or you have to communicate between these processes if you have two cache writes in flight. And the networking radio is another example of this. We have limited bandwidth, and we have some requests that might be high priority and some requests that might be low priority. And if those are going to two separate places, we have to rely on our operating system primitives for prioritizing requests, which is not ideal all the time. So with all that in mind, let's get started. Let's code. So Swift. What is Swift? Swift is a language that has protocols. Protocols are these cool things that many of you may not be familiar with. But you can think of them as like a blueprint that can be adopted. It's kind of like an interface or a trait in other languages. And it has some nice features. One of them is called associated types. And so in this case, we want an associated type for a key and associated type for a value. And what this means is it says, any concrete type that implements the protocol, the cache protocol, has to provide a key and a value, okay? But at this point, we don't know what they are. And now we can think about what do we want our cache to do. Well, we want to be able to get a value given a key, okay? But that operation might be slow. So instead of returning the value, we're going to return a future of a value. And for those that aren't familiar, think of a future as a value that represents some asynchronous computation that may or may not be completed, and it can fail. And additionally, we can chain transformations onto this future, on success or on failure, and we get back new futures. And you'll see how that's used in a bit. But think of it just as like an asynchronous piece of data. So set, another thing we want to do. Given a key and a value, we want to write to the cache. And this might be slow, so we put it behind a future. But we don't care about the value, so we just use void. Okay? So now we have a protocol. We can create instances. All right? So here's a RAM cache. We're generic on K and V as long as the keys are hashable. So that's that where clause there. And we're going to bind key to K and value to V. That's what the type alias keyword does in Swift. And our get method is just going to look up this key in a hash map. That's why we want the keys to be hashable. And our set method can write to the hash map. Okay? Pretty straightforward. For disk cache, we're generic on K, okay, as long as the keys can be converted to strings. And we'll bind key to K, and we'll bind value to a byte array, which on iOS is NSData. And what we're going to do is we're going to MD5 hash the string, the key, and get a file name. And then we're going to use that file name to look up the bytes in the file and to set bytes to the file. Okay? So we have our two caches. Now we have RAM and disk. But this isn't what we want. Okay? At the application layer, I don't want to have to think about going through my layers to get to my value. I just want to query one thing and either get a value or fail. So what we want to do is we want to stick them together. So this is a picture of two things stuck together, or a kite or something. We can take this and turn it sideways, and we have this process. So a key comes in. Oh, no. Thank you. Okay, I hope nothing else. Tell me if something else is cut off. Okay, so a key comes in, we check RAM. If it's there, we return the value. That's the violet arrows in this diagram. If it's not there, you follow the gold arrows. We check disk. If it's on disk, we write back to RAM, we return the value. If it's not on disk, we fail, right? So nothing about this depends on RAM and disk, so let's just erase that. And as long as the keys are the same type, because we might fail on the first one, so we have to check the second one. As long as the values are the same type between the two caches, because if we do succeed on the second one, we have to write back to the first one with the same value, then this process can type check for any two caches, okay? And if we want to hide this process from consumers of this API in their application logic, then what we can do is we can take this whole process and wrap it inside a cache, okay? And now we have a cache that you can give it a key, gives you a value, or it fails, right? So that's pretty cool. Let's implement it. So I hope this doesn't cut off. In Swift, we can use extension to add methods to any classes that implement protocols. Okay? So we're going to add a compose method onto here. I'll explain the signature in a sec. Don't be scared. What this is going to do is it's going to add a compose method to any class that implements cache. Okay? So, excuse me. So what does this do? It says, first of all, it's a method, so it acts on some cache, and it takes another cache, which has type B as a parameter, and B has to be generic because we want to be able to combine RAM and disk, for example, and those are two different types. Okay? But this only works in the case where the keys are the same and the values are the same. That's the where clause at the bottom. And due to a limitation in Swift's type system, we're going to return a basic cache, which is just a dumb wrapper around the get and set methods, such that we can pass them as lambdas. Okay? So to implement this, we pass a lambda to get, and this function takes a key, and it first checks the first cache. That's the self.get, okay? That gives us back a future. If that future succeeds, we return it. And if it fails, then we execute the closure on the right. That's what the or else operator does on futures. So if we missed on the first cache, then we try the second cache. It's the other.get. If that succeeds, then we can map over the future, and then we can take the resulting value and set it back to the first cache before returning it. Okay? And then set takes a key and a value, and it writes to the first cache, and it writes to the second cache in parallel. This is mostly going to work in all situations, and it will work for all practical situations, but John Hughes pointed out to me that there is a flaw in this, in set in particular. If you take two caches and you compose them, and you take that cache and you compose it with one of its constituents, then your composed set behavior gets really weird and everything breaks down. So don't do that, and you don't have to do that with this framework. So I'm kind of hand-waving here, but if you're thinking really carefully, you might find where things break down. So this is compose, okay? Now we can use it. We can take some cache A, and compose it with some cache B, and we get a cache C, all right? And this C is a cache that we can get and set, which is cool. And that's not all. We can add another cache. We can compose with another cache X, and we get back C, a cache, right? And in our example, we have RAM and disk, and we actually do have a third cache that is useful. So we can model the networking layer as a cache that always misses, so to say. So the get, where our keys are URLs, and our get method of our cache hits the network for the resource and gets back bytes. The set method would just null up. And you could implement a network cache where the set method actually sent data to your backend, let's say, but usually you don't want that. So now that we have three things, we have a decision to make. Compose acts on two caches, but we want to combine three things. So we can first combine RAM and disk, and then the network. Or we can combine disk and network, and then put RAM at the front. Okay? And if you think about it, and you draw a really large picture, then you can prove to yourself that these are equivalent. And I'm not going to show that here, but you can draw it yourself. So these are equivalent, which means that this compose operation is associative. Okay? And then we can consider this cache, a cache that always misses. So there's no violet arrow. It's just a gold arrow. If we have this cache that always misses, I'll call it the identity. And we take the identity and we compose it on the left. That's the top diagram. When a key comes in, then we'll go to the real cache that we're composing the identity with, and it'll either succeed or fail, as it would if we hadn't composed anything at all. All right? In the second case, our real cache is at the front. A key comes in. If a value is there, we return it, just as we would have done if we hadn't composed anything. And if we fail, then we'll fail again, just as we would if we hadn't composed anything. So because identity behaves like this, all right, and because we have an associative binary operator, then we have a monoid. This is what a monoid is. So if you didn't know, consider yourself illuminated, I guess. Is that the right use of that word? Okay. So monoid. Monoids are cool. They're really awesome. I love them. You can do interesting things. Now, in the context of caching, we can smash together a bunch of caches. We can start with the identity. We can combine with RAM and disk and network, and we get back just a single cache, an image cache that does all the things we want. Or we can choose to compose disk and network first because our compose operation is associative, and then we can store that in a variable and reuse it across our entire application, across all of our cache stacks, which is really, really useful. But we're not quite done. Okay? So if you recall, our disk and our network give us bytes, but for image caching, for example, we don't want to deserialize a JPEG image, for example, in the memory layer because it's too expensive. So we want to store uncompressed JPEGs, like bitmaps, in our memory cache. And same with like our models, right? We have JSON data on disk, but we don't want to store JSON data in memory. We want to store the fully parsed, structured data in memory. So we have this type mismatch here. Remember, I said the values needed to be the same between the two caches for a compose operation to work out. So it's like we're trying to combine a circle and a triangle, and that doesn't work. So we need to make it work. Let's do some magic. Let's transform caches, okay? So given a way to turn circles into triangles and a way to turn triangles into circles, if I have a cache that gives me circles, and I want a cache that gives me triangles, then I should be able to have it. And you do need both transforms. I'll show you. For example, we have a way to turn bytes into a bitmap, which on iOS is NSData and UI image. And we have a way to turn a bitmap into bytes. And I have a cache that gives me bytes. Then I can expose a view of that cache that gives me bitmaps, which I can then compose with a memory layer with this map values transformation. Okay? So just want to point out these transform caches are like kind of virtual. They provide a projection on the same underlying cache. We haven't actually changed our disk cache to store bitmaps, for example, which would be too expensive. We want to store JPEGs. But we're able to view it as if it stored bitmaps by hiding this transformation. So in a picture, we have this cache that stores JPEGs, and we have transformations forwards and backwards, and we can wrap it up in some wrapping paper that looks like a triangle. And the types will work out. So let's implement it. We have a way to turn circles into triangles and a way to turn triangles into circles. We have a cache that gives us back circles. We have to subvert Swift's type system, so we're using basic cache, and it's going to give us back a triangle. So let's implement it. Get. We have a key. We access the original cache, and we get back a future of a circle, and we need a future of a triangle. So we can take that future of a circle and map over it with our circle to triangle transformation, and we get back a future of a triangle in this type checks. And then our set, here, this is the new cache. So we're given a key and a value, and the value is a triangle. And we have to write it back into a cache that accepts circles. Okay? So we need the inverse transform here. And that's why we need both, the forward and reverse transform. So of course, there's nothing that ties us to circles and triangles, so we can do bytes and bitmaps. And there's nothing that ties us to bytes and bitmaps, so we can just make it generic. And this works for any two values. Okay? So this is how we transform caches. If you're a Haskell person, you can think about the functor going on over here. It's not quite a normal functor, right? Because we need both transforms, both the forward and the reverse transform. So this is actually an invariant functor with respect to the value. So on just the value, you need to provide forward and reverse transform to transform it. If you don't understand this slide, it doesn't matter. But if you do, maybe it's interesting, especially this next part. So if you add a phantom type parameter and you type alias the cache to, if you type alias that type parameter to the original value, then you have a profunctor instance and all the laws work, which is cool. If you don't understand that, it doesn't matter. So key transformations. So what do we need to do? We need to take a cache that accepts keys and return a cache that accepts some key K2. Okay? Here we only need to provide a reverse transform. All right? So here, if you think about it, we're returning the new cache, so we're given the new key, and we need to store it. We need to query the old cache, so we need to provide a reverse transform. All right? In set, we're given the new key, and we need to set into the old cache. Okay? Good? So we only need the inverse transform here. If you're a picture person, if we have a triangle to circle, we have a cache that accepts circles, we can expose a view of that cache that accepts triangles instead. And if you want an example, our disk cache likes strings, because we're going to MD5 it, and our network cache likes URLs. So in order to put them together, we might want to map the keys of our disk cache into some cache that is, or some projection of the cache that exposes a view that accepts URLs. And so we can provide a reverse transform, a URL to string, and we get back a cache that takes URLs as keys. Okay? Hopefully you followed that. And you can ask the question again. Don't listen to me if you're confused about this part. What functor do we have here? We don't have a standard functor. because we don't have a forward transform. We only have a reverse transform. So we have a contravariant functor with respect to the key. Okay, so caches are kind of cool in this way because it's a pro functor if you use the value as the parameter, and it's a contravariant functor if you use the key as a type parameter, as your functor real parameter. I don't know how to say it. So it's kind of cool. Now we can put things together, and life is good, and that's good, right? We can associate disk and network together, and we can put them together because we have the key transformation, and then we can put the memory layer on top after we have done a transform, after we've done the bitmap transform, so that we don't do the expensive computation of decompressing images over and over and over again. And the code for this is 3 lines, which is cool. And this is what it looks like in production, which is awesome. It's 3 lines, 3 to 5. So we have a disk cache. We compose it with our networking cache. We have some disk and networking cache value that we use across all of our stacks. And then in this case, we're going to map over the disk and network and transform it into some view that accepts bitmaps. And then we're going to compose it with a RAM cache that accepts bitmaps. And now this thing is something that we can use in our application to query for images, which is cool. So that's good. But there's a problem. So here's a real example, right? So we're building a messaging app. 2 users are messaging each other, and they have their avatars, their profile pictures next to their messages. If they each have sent 10 messages to each other, and we're opening the app for the first time, and it's a clean install, then if you think about it, concurrently, 10 requests are going to go in, and they're going to ask the memory layer, do we have this image? And they're all going to fail. Then 10 requests are going to go into the disk layer, and they're all going to fail. And then 10 requests are going to go into the network layer, and they're all going to hit the network for the same URL. So that's bad. We don't want to hit the network 10 times here, right? That's very bad. We only want to hit it once, or if you're thinking about both profile pictures, twice. So what we want to do is we want to reuse in-flight requests. So let's do that. So what we can do is we can say, for all caches, everyone who implements the cache protocol, if your keys are hashable, then this reuse in-flight request method will be available to you. And what this does is it takes a dictionary that maps keys to in-flight requests, which are just futures, and it's going to return a view of that cache with the types the same key and the same value, where our get, instead of just asking the cache for the value, we're going to check the dictionary first. And if it's there, then we're done. And if it's not there, then we can make the request to the cache and store the future in the dictionary for future accessors of this cache. And set is the same. And if you ignore some extra logic for freeing memory and maybe some atomics to make this thread safe, this is basically the implementation. It's completely decoupled from the idea of networking, which is really, really nice. Okay, we can take this, reuse in-flight, and apply it to our network cache, and now we get a smart network cache. And the smart network cache, when we get the same URL twice in short time proximity, then we only get back one future. It's the same reference, right? So we've only made one in-flight request. So we solved the problem. If you're thinking to yourself, if you've ever made a mobile app before, or done something with a front-end application, you may be thinking, like, all caching libraries provide a solution to this, right? Now, the interesting thing about this particular solution is that, like I said, it's completely decoupled from the notion of hitting the network. So what we can do, which most caching libraries cannot do, is we can take this, and instead of applying it directly to the networking layer, we can apply it to the composition of the disk in the networking layer, right? So now, if there's a request in progress, like querying the disk or reading something from disk, we can reuse that future. If it's in between the disk and the network, we can reuse that future. And if it's in the middle of the network, we can reuse the future, which is really, really useful. And this same technique applies for any sort of cache-agnostic operations that you want to do. For example, concurrency throttling. Like, if you want to say only 5 requests at a time can be processed by this cache, you can define it in a way that's agnostic of the underlying cache, and then you can apply it to compositions of caches, which is really awesome. So now we just add this reuse in flight to our first line, and this is our cache stack for loading images. And that's it. It's pretty cool. So what we've done, right, is we've taken this inherently complex problem of caching that is usually solved in 5 different ways across your app, let's say, or on your back end, where you have one imperative disgusting place where you do image caching, and one imperative disgusting place where you do video caching, and one imperative disgusting place where you do model caching, if you're stuck with APIs that are imperative. And we've taken that and we've minimized the surface area so that we only have to deal with the imperative APIs for networking in one place, wrap it up in a nice wrapper, and then reuse that across our application. Excuse me. So it's pretty awesome. That's good. We can do it now. We can compose our disk and network together first. We can compose with a RAM layer that is a decompressed bitmap, for example, because we can do transformations. And we can apply transformations to caches or composed subsections of our layered stack of caches by writing these extension methods. Sorry, I'm pretty thirsty. OK, that's good. We did it. Now, if you want to use this and you're writing Swift, which maybe one person in this room is, hopefully, there's this library called Carlos that implements these ideas, and it is open source. Some of the names of the methods might be a bit different, and I don't think the documentation shows some of the formalisms that we went over, but it's pretty awesome. It was created by Vittorio and Isad, and their Twitter handles are here. There is a PureScript implementation that I made to help myself formalize the profunctor and the contravariant functor and the monoid. So there's a link there, and I'll give a link to the slides. And that's it. I'm Brandon. That's my Twitter, my Pinterest, a link to the slide deck, and a thank you. So, you can clap. I think there's time for questions. Great. All right. Thank you. Thank you so much.
Which features library did you use? Did you roll your own? Did you use bright features or promise or something?
This is, OK, so what I would like to use, what I would have liked to have used is bright features. I think the bright features implementation is quite good. In this slides, I used pseudocode. I didn't use the exact methods from bright features. Carlos, the implementation of this library, has rolled their own features, and they're a little bit different. They have this notion of cancellation as well. But in my application, I wrote an adapter between the two, so I didn't have to think about it. But.
Did you think about batching, like when we manage queries? Like
actually wait for the mic, so we get that recorded.
So did you think about batching when you get like many queries within like a short time frame and can send them at all? Like
Yes, that is one of those cache agnostic transformations that actually exists in the Carlos library.
Okay.
So yeah, it's awesome. But yeah, it's an example of one of those things that you write in a few lines of code that can be used across any subset of your caches, your cache stack. Yeah.
Your cache structure looks
Usually like a functional lens.
Yes.
Can you look into how to harmonize those two structures?
Sorry, say that last bit again.
Can you look into how you harmonize
your
I think that in a sense, it kind of is a lens because it's a profunctor, right? So if you go to that profunctor optics talk later today, then you'll see that. I haven't actually done that work myself, but there's definitely something interesting there. But it's a lens under a monad. So it's some optic, I don't know the name. I'm sure there's a name for it. Yeah.
What about cache invalidation? Does this help with cache invalidation and how?
Yeah. So so cache invalidation. So I'll tell you what the Carlos library does, which works well enough. So the interface to cache, I lied and I showed a simpler implementation. There's also this extra method that's quite ugly, but it's kind of useful, which is just on memory warning, which is when the operating system tells our process that we're using too much memory. And so any cache can react to that callback to clear itself. So you want to do that for any cache that uses a lot of memory. And then the internals of the disk cache would, whenever like a new value needs to be written, you could implement some sort of like LRU, least recently used cache eviction strategy, and that's sort of an implementation detail of your cache that you hide behind the interface. So did I answer your question?
Yeah, maybe this is more in the backend part, but if you have like, if you, for example, change the update, so you have something you want to push
Yes.
validation, and you want.
Yeah, so that is an interesting problem that doesn't come up that much on the front end, so I haven't thought about it, but I bet there's some interesting, cool work to do in there. Yeah, you should check it out. Any other questions?
I had a really basic question. The microphone doesn't work, don't even bother walking back here. Back on the very first slide where you showed an example of your views with F and F inverse.
Yes.
It's a silly thing. I'm not a Swift programmer, so that one had it too. But
Sure.
there's this underscore there in front of F inverse.
Yes. So Swift. So actually, to be fair, so there's a long story here. Swift moves fast. So I'll repeat the question. What is this underscore? Okay. The Swift language has breaking changes with its syntax every version. In the version of Swift that existed when I first wrote this slide, Swift actually does something unique that many languages don't do, where when you invoke functions and methods, you provide the name as well for your parameters. In the latest version of Swift, you are supposed to provide names for all your parameters. In the version of Swift that existed when I wrote this particular example, sorry that I didn't update it, the first parameter's name is omitted when you're invoking the function, but the second parameter and the third and all subsequent parameters require you to pass that name, and which is really nice. It's like an extra bit of documentation that you get in your type signature, and in your, not in your signature, I guess, in your invocations, so that you understand what is going on. But in this particular case, when we're mapping our values, it's not useful to say, at least I didn't think it would be useful to say F and F inverse. So the underscore says, I don't need to provide that name on invocations.
So that's suppressing the name parameters feature.
Yes.
Okay, thanks.
Any other questions?
Only like the whole cache structure seems to be like homogeneous. Like you only can store like one size value within one cache. Is there some like, did you put some thought into making it heterogeneous, like storing different values?
Yeah. Well, so the way that I did that. So if you remember, the disk and the network layers reused across all my cache stacks, and those all are storing different types. But basically, if you provide sort of a I don't know if it's the upper bound or lower bound, whatever. But so basically, at the lowest level, the disk and the network, they deal in bytes. So as long as you provide a way to serialize and deserialize, then that can store everything. So that's how I accomplished that particular bit. And I think it's just, like, if you can find a type, like if you want to store 3 different types of things, 3 distinct things, then the type of your value would be like an algebraic data type with 3 cases. And you just provide a way to, either in memory, you can just store it, or if you provide a way to serialize and deserialize, then it'll work. Any other questions? Are we out of time? All right.
Thanks to the speaker again. Next session in 10 minutes.
JSON on disk and JSON over the network. Okay? But in all these cases, we have this same sort of structure. We have these individual pieces that we're stacking on top of each other. And you know, in the video case, we only care about the disk and the network. In the other cases, we care about that extra RAM part. But I've drawn the boxes in this way for a reason, because it's not just useful to treat the disk and the network as you know, one type that you can instantiate multiple values for, but it actually makes sense to have one instance of our disk and network layer and share that across all of our caches in our application. And reason for that is that for inherently shared resources on your system, if you have one instance, one thing in your application communicating to that resource, things become easier. Sorry for the delay. Looks good. All right. Hi. I'm Brandon. I'm an engineer on the iOS core experience team at Pinterest. And today I'm going to talk about composable caching in Swift. And if you don't know Swift, it's OK. If you're using a functional language that's decent, you can do all the things that we're going to talk about here. So why do we care about caching? Getting stuff from the network is slow. Getting stuff from disk is a little bit faster. Getting something from memory is very fast, but we have very limited memory, limited disk. So when we actually want to retrieve something big, or something where latency is important, we want to associate it with a key, and then make this more clear. So disk, okay? For our cache, let's say, our disk layer of our cache, we only want to store 1 gigabyte, okay? If we have one single object, let's say, that is responsible for writing to that gigabyte of space, when we get up to the edge, you know, we know what to do. We know when we're over. We know when we're about to go over. If we have multiple managers talking to our disk, then when you get close to the gigabyte, you either sacrifice correctness, if you're OK with going over a little bit, or you have to communicate between these processes if you have two you know, cache writes in flight. And the networking radio is another example of this. We have limited bandwidth, and we have some requests that might be high priority and some requests that might be low, and store it in these layers. And when we retrieve it, we go through this process. Okay, so a key goes in. We first check memory. If it's there, we return the value. If it's not there, we check disk. If it's on disk, we write back to RAM and we return the value. If it's not on disk, then we hit the network. If hitting the network fails, then we fail. If hitting the network succeeds, then we write to disk and we write to memory and we return the value. Okay? And sorry, this is in the context of like a mobile application, right? So we're getting, let's say, an image. Okay? But the same sort of process works on the back end as well. Okay? So key goes in. We might have some map, some dictionary on one particular machine. If it's not there, we might fall back to memcache, which is shared across a bunch of servers. And if it's not in memcache, then we might have to make an expensive RPC call to our data store service. But at the same time, you know, whenever one of the layers succeeds, we write to the layer above, right? So let's look at more examples. Okay, image caching. URL of an image is the key. We look for a bitmap in RAM, and we look for a JPEG on disk before hitting the network. For video caching, if you're doing stuff on, if you're making an iPhone app, for example, the memory layer is handled to you by your framework. So you only need to care about the disk. So in this case, we only have a disk above a network. But even model caching can be thought of in this way. So for this example, we have a user profile, and our key is a user ID. We look up the structured profile data in memory, and we fall back to